Hello everybody, welcome to another Henstitute video. This one is on electric circuits and specifically Kirchhoff's rules. Gustav Kirchhoff came up with a lot of work dealing with electric circuits, but this one's kind of neat because now what we're going to start dealing with is circuits where you may have more than one voltage source or where you have different currents flowing in it. It really breaks down into two rules. The first one is known as the junction rule. And we've already been basically using this when we talked about things like series and parallel circuits. If I have a certain amount of current going into a junction, I have to have that same amount of current coming out. So if I have 7 amps going into this junction and 5 amps goes this way, 2 amps has to go that way. So 5 plus 2 equals 7. So that's kind of an obvious one. The next one is what's known as the loop rule. And what it basically deals with is if you look at a loop of current, you should have all of the voltage rises, in other words, all of your voltage sources should equal all of the voltage drops. And the way we also want to look at this is in terms of going from positive to negative. So if I come through on a certain direction on this, we should have the voltages being drops as opposed to rises. So if you notice, if I go from positive to negative for our voltage source down here, 12, and I have 2 amps going through here, I know 2 amps through here, that voltage equals current times resistance. So therefore, if I have 2 amps times 5, that's going to be 10 volts. Oops. And that's how much that one is dropping or using. And then 1 times 2 is 2 volts. Guess what? 10 plus 2 equals 12. So they sound very simple. And it really kind of breaks down into those two ideas. It's more of how do you apply them. And so we kind of have a reasoning strategy when we're applying Kirchhoff's rules. The first thing is you want to draw the current in each branch of the circuits. Choose any direction. If your choice is incorrect, the value is going to basically just come out as negative, but you know that you have picked the wrong direction. They suggest in the book, or some sources will say, mark each resistor with a positive and a negative at the other end in a way that is consistent with your choice of current. I personally don't think you need to do this because as long as you have picked the current, we already have that kind of positive and negative. So I just kind of ignore that one. Then we apply the junction rule and the loop rule to the circuit, obtaining in the process, you end up with these different equations. And therefore you can find your unknown and then you just solve them simultaneously. So let's look at one example. This is a very easy one. It says determine the current in the circuit. So what I have here is I have 24 volts connected with these different quantities. I also have a 6-volt battery. So one of the things I did is we've designated a direction for the current. Let's assume that the current flows in this direction. So it's flowing to the right through this 12 ohms. It's here, it's actually flowing from right to left through here, and then it's flowing this way, and then it's flowing through here. So whenever we're doing this to try to figure this out, this one I know it says the loop rule. I'm actually going to start off with that idea and kind of work my way through. I don't have to do the junction rule in this one because I don't have any junctions. I don't have any splits. If this at A had split off into another, then I would have some junction, but I don't actually have that here. So for this one, if I think about it, all of the voltage rises. And basically what that means is my voltage sources. Now, my first instinct is you would go, oh, it's going to be 24 plus 6. However, the way I kind of define it to people is look at your current. If your current comes out of the positive on a voltage source, that's the right direction. So therefore, it's positive. However, if it comes out the negative, so notice on this one, and the way batteries are always drawn with the schematic is the long line is the positive and the short line is the negative. Since it comes out the negative on this 6-volt battery, it means this battery is basically connected backwards. So I'm actually going to put this in as negative for my rises. So the sum of all the rises, or the voltage sources, the way I like to think of it, should equal the voltage drops. So how do I find the voltage drops? Well, here I have I times 12. So remember, the voltage equals current times resistance. So the voltage drop here would be I multiplied by 12 ohms. And then plus, I have the current going through this one, and this one happens to be 8 times I, or I times 8. Since I only have one current, this gives me an equation. 24 minus 6 is going to give me 18. And then I have 12I plus 8I, so that's going to give me 20 times I, and then I could just divide by 20 here. And that should give me my current, 18 over 20, which I can simplify down. That's going to be 9/10, or in other words, 0.9 amps of current. So that's the way I do it. If you look, I'm going to show you the next slide. They kind of write it slightly different. Now, the reason why they write it slightly different is rather than put that I'm adding the other voltage source as a negative, they put that as a potential drop. And the reason why they put that as a potential drop, again, because I picked the current going through it backwards. In the battery, if you go from positive to negative, that's backwards. But if you go from negative to positive in the battery, that's actually correct, or that's the rise. So it's rising in energy or it's dropping in energy. That's the way we kind of deal with it. That pretty much kind of sums things up. I will take a look at a sample problem like this one. So this is a reason that we might need to know something about Kirchhoff's rules. We have a battery in our car that's connected to not only the alternator, but also your headlights. So you have two different voltage sources you have to kind of figure out. So here you would have a current going through the alternator, a current dealing with the battery, and you have a current dealing with the headlights. So we'll take a look at this sample problem later. I'm going to add this in as another little example and see what we can kind of figure out. I hope you enjoyed this little edition of Kirchhoff's rules.